Okay, so we have our last lightning talk session of the day. So we're going to have 3 talks before our discussion time. And our first talk is from Dionisio, who's going to be talking to us about detectors.
Thank you. And thank you for the invitation to participate here. I will talk today about several of our detectors, but I'll focus on one of them. For that, I'll talk a little bit about our vision, the PIC-UHR, which is our generation of 35 to 100 kiloframes per second detector, how that impacts the data from our point of view, and some of the things that have been discussed in the panel in terms of how we take advantage of that. This is the family of detectors that we have. So starting from LCLS-I, where everything was sort of easy, 120 hertz, send the data out, save everything and do offline things, to where we are now, which is between LCLS-II and LCLS-II-AG. These are 5 kiloframes per second, turning into 35 kiloframes per second, and then being, let's say, one-to-one compatible with our 100 kiloframes per second. Then I wish I had more of these 8 minutes to talk about the SparkPICs. This is a family of detectors that actually involve information extraction at the ASIC level. So this is where we're studying some of this analog compute, where we're studying some of this data reduction of classical aspects, sending low resolution, then receiving triggers, sending high resolution, and all of the different things that we can do at or very close to the edge. And another 8 minutes I'd like to have for the Morpheus, where we say, hey, this is the data-driven part of the research, where we actually are looking into the data using AI ML to actually feed back into the system and adapt the system. What if we can send data at a lower resolution, depending on where we are in the experiment, versus a high resolution, or versus a different number of pixels, or different things that we can change in terms of gains and things like that. So this is yet another family of detectors. Today, I'll focus more on the 35 to 100 kiloframes per second. This is full frame readout. We do that in sort of a very defined strategy with integration with the scientific needs, scalable. So we go from very small to very large detectors, platform-based. We use a lot of the same standard interfaces, so we can build the bigger things, but they look exactly the same as the smaller things from the compute point of view. And today, I'll talk more about some of the ideas about the experiment-specific and innovative as part of the intelligence aspects. This is an example of the PIC-UHR, how it's built. So it's a silicon sensor, hybrid pixel detector, so it's bump bonded to an ASIC. The ASIC then sends the data out through several gigabit transceivers. These gigabit transceivers then, or these modules are then put together. This is what we call the 2x3. It's because it has 6 ASICs for one sensor. This module already has an FPGA in there. And that is the first place where, let's say, after the ASIC, data can be processed. And I will show an example of how we're doing that right now. But also, this is a way where we can use the programmability of the systems to push for different types of compute to be there at the streaming level. So before it reaches the next level of compute. We built these detectors in 1 megapixel tiles. And then these are completely independent tiles, meaning that they have their own cooling systems. So this is CO2 cooling system, so consumes a lot of power to generate these rates. It has its own power supplies. It has its own data, external data transmissions using different fiber optics. And then we build megapixels, 4 megapixel detectors that are 4 of those. And in line with that, we have also a 16 megapixel version of that, also running at 35 to 100 kiloframes per second, because it's more of this 1 megapixel tile. So everything scales linearly with that. These are some of the parameters of the ASIC design and how much data each one of these ASICs sends out, and some of the technology nodes. This is a simple case where we are embedding into this first level FPGA some pre-processing. So this is the block diagram at the detector FPGA. We also have the block diagram of the PCIe cards. So these two cards are actually 2 kilometers apart. So this is at the hutch taking data. This is at the server right next to a GPU where a DMA engine can be used to send the data directly to the GPU from the streaming mode into the next level of compute. So what we're doing now is very, let's say, low-level corrections to the data. So we're using HLS, which is one of the methods that you can program these FPGAs to do dark subtractions, gain corrections. Then we send it over from the 2x3 tile to the PCIe over 2 links of 100 gigabits per second. So it's a lot of data that goes over. We correct it a second time, so we can actually have calibrated data, and then we send it through the DMA. So one way of doing more of programming. Of course, this generates a lot of data, but not necessarily we're aiming for data. We want actually information. And I think to the point that the panel actually made is that we have or advocate for a distributed system where different parts and different hardware can actually have different types of feedbacks, but also they can focus on different types of operations, and therefore thinking about a distributed system where the different compute nodes perform different tasks, and those different tasks enable a system level optimization is one of the things that I think we're pushing for, and we're designing the system for that by attacking the problem at the ASIC level, attacking it at the FPGA level, inside the detector, as well as the first, let's say, edge processing nodes, and also at the final system. This is my last formal slide, which means we are also involved in looking at how can we use the ML in the FPGAs to process the data in streaming modes. We use a library that is called SLAC Neural Network Library. This is a library that is coded, as Ryan was mentioning before, in a C++ templating code that then can be traced into or can be programmed into the FPGAs. Here is an example of an application of our serial crystallography study case that we are developing right now. It's a hit, maybe, or miss classification. So the way we are implementing that, we're doing the pre-processing or part of the pre-processing at the detector FPGA. Second part of the pre-processing actually happens on the AI FPGA or the edge FPGA at the server level. And we now have an example of a CNN style that does this type of classification. This would be an example of where you can do data tagging, meaning you send your frame together with what this small FPGA thinks the data is. It's a hit, then the PC can say, hey, I will evaluate that to the full extent. If it's a miss, I probably will save some of that data because I want to make sure that I'm classifying it properly. If it's a maybe, well, then depends on who is programming the next level to say, what do I do in this case where I'm not sure? But this is an example of where we're sort of pushing for heterogeneous systems with ML distributed in this way to augment the things that we can do on the next level up. It's not necessarily proposing to solve the whole problem, no, because it's very limited. The models that we can put here are very small models, but I think this tagging can enable, as I think was discussed on the panel, to steer the next level of compute. And I'd like to thank you all for showing this, and just to leave with one message that this is actually coming together. This is an example of this 35 kiloframes per second detector taking data at MFX, and this is how the data looks on the multiple gains when we reconstruct in a single gain, and it is capable of doing single photon as well as 10,000 photons per second detection per pixel. So just as a sort of, it's real action.